Machines that turn one sequence into another, like translating English sentences to French, power many modern tools. For years, the strongest systems used recurrent neural networks, or RNNs, which process one word at a time in order. This sequential processing is slow on modern hardware because you cannot compute all positions in parallel. An RNN also struggles with long sentences. An early word like making must pass its signal through every intervening step to influence a later phrase like more difficult. This lesson explores how the paper Attention is All You Need solves both problems by building a model called the transformer that uses only attention mechanisms, replacing recurrence entirely. We will walk through the problem space, build up the architecture step by step, and then examine the results and how this model relates to earlier systems. Consider translating. Making the right decision early in the process can save significant costs, though it often makes the initial planning phase more difficult. The word making near the beginning and the phrase more difficult near the end depend on each other grammatically. In an RNN, the hidden state must carry the signal from making through every intervening word, creating a path length equal to the sentence length. Learning to propagate useful information across 15 or 20 steps is challenging, and the sequential computation means each training example is processed one time step at a time. A purely convolutional approach improves parallelization, but relating two distant positions still requires many stacked layers, making long-range dependencies hard to capture. The goal is a layer that can relate any two positions in a constant number of sequential operations, processing all positions in parallel while still modeling order. A sequence transduction model has two parts. The encoder reads the source sequence of tokens, such as English words, and produces continuous representations called embeddings, which are learned vector mappings from discrete tokens to dense spaces. The decoder generates the target sequence one token at a time. This is autoregressive, meaning each step depends on previously generated tokens. Modern GPUs excel at parallel matrix multiplies, but RNNs cannot fully exploit this because each time step requires a separate operation that depends on the previous step's result. The core idea of attention is simple. When generating the next word, the model should look at relevant parts of the source sentence. For the French word chat, the model should focus on the English cat and ignore other words. This soft alignment assigns weights to each source position, and the weighted combination becomes a context vector for the decoder. The transformer uses scaled dot product attention. Suppose we are translating the cat sat to French, and the decoder is about to produce the word for cat. The decoder has a query vector representing what it is looking for right now. The encoder's outputs for each source position serve as key vectors and value vectors. The idea is to compare the query to every key to get a compatibility score, then use those scores as weights to average the corresponding values. For a single query and a set of key value pairs, compute dot products between the query and each key, then scale by dividing by the square root of d subscript k, where d subscript k is the dimension of the keys. Apply softmax to get attention weights, and the output is the weighted sum of the values. In practice, we handle all queries simultaneously by packing them into matrices: Q for queries, K for keys, and V for values. The formula is attention of Q, K, V equals softmax of QK transpose divided by square root of d subscript k all times V. The scaling factor prevents the dot products from becoming too large, which would flatten softmax gradients and make learning difficult. Rather than performing a single attention function, the transformer uses multi-head attention. The idea is to project the queries, keys, and values into h different lower dimensional spaces using learned linear projections, then perform attention in parallel on each projected version. This produces h output vectors, which are concatenated and projected again to produce the final output. With h equals 8 heads in d subscript, k equals 64 for each head, the total computational cost is similar to single-head attention with full dimensionality. Different heads can learn to focus on different types of relationships, such as syntactic dependencies versus semantic similarity. Multi-head attention allows the model to jointly attend to information from different representation subspaces at different positions, which is more powerful than a single weighted average. The transformer applies multi-head attention in 3 distinct ways. First, encoder self-attention. Each position in the encoder can attend to all positions in the previous layer of the encoder. This allows the model to learn relationships between words within the source sentence itself. Second, mask decoder self-attention. Each position in the decoder can attend to all positions in the previous layer of the decoder, but only up to and including the current position. This masking prevents the decoder from cheating by looking at future tokens during autoregressive generation. Third, encoder-decoder attention. Queries come from the previous decoder layer, while keys and values come from the output of the encoder. This allows every position in the decoder to attend over all positions in the input sequence, mimicking the traditional attention mechanism that aligns source and target. Since the transformer uses no recurrence and no convolution, it has no built-in notion of token order. To inject positional information, the model adds positional encodings to the input embeddings. The paper uses sinusoidal functions. Position pause is encoded using sine and cosine functions of different frequencies. For each dimension 2i of the encoding, the value is